fix komputer. Oke, Assalamualaikum warahmatullahi wabarakatuh. Hari ini aku buka buat eh, sesi lab modul 2 untuk kelas struktur data. Di sini kita bakal membahas tentang kalian udah tahu nggak materinya bakal apa aja, guys? Oke, kita buat sekarang kita bakal belajar apa itu tentang pengenalan tree sampai set dan map. Aku share screen sebentar. Jadi buat materi ini bakal seperti yang udah tak jelasin pas itu, kita jelaskan yaitu kita akan belajar tentang tree. Kita bakal ngulang beberapa materi, tapi kita cuma cepat aja yang udah kita pelajari. Soalnya ada beberapa materi yang belum kita pelajari. Nah, kita ulang lagi sedikit tentang tree. Apa itu tree? Tree itu salah satu bentuk struktur data nonlinear. Kalau misalnya kita tahu array ya kan, array itu sesuatu data yang linear kan. Kamu cuma bisa satu dimensi atau dua dimensi, tiga dimensi kan. Kamu bisa cuma bergerak sesuai dimensi itu. Lalu, oke, nah apa itu? Sedangkan tree dia itu pasnya itu belum semuanya belum tentu bisa diakses satu sama lain. Jadinya kalau di contoh ini adalah satu contoh tree ya kan. Kalau misalnya kita lihat di sini dua di sini itu bisa mengakses ke 5, 9, dan 4. Tapi 5 tidak bisa mengakses 10 dikarenakan kenapa? Dia tidak terhubung. Tidak punya path untuk ke 10 ataupun ke 6 ataupun ke 5 lainnya ataupun ke 11 karena tidak ada pathnya. Begitu. Jadinya bisa didefinisikan sebagai kumpulan node dengan elemen khusus yang disebut dengan root. Ini adalah rootnya atau kayak akarnya. Kalian semua untuk mengakses tree itu bakal mulai dari root ini untuk pertamanya pasti. Dan apa itu nanti itu kalian bakal melakukan apa yang disebut traverse. Traversal itu jadinya kalian mengunjungi uh, node di sini itu sesuai dengan apa yang path yang telah ditentukan. Oke. Nah, untuk terminologinya kita sudah pernah membahas ini. Kita ada yaitu root tadi, adanya ancestor untuk parent yaitu adalah node sebelum dari node tersebut. Jadi misalnya di sini B ya. Kalau misalnya kalian kelihatan di sini, oh my god, uh, oh my god. Nah, sorry. Di sini tuh kalian ada ancestor atau parent. Parentnya di sini itu uh, Jadinya B ini itu parentnya atau ancesornya adalah A, C juga, D juga, sama juga dengan E, parentnya itu adalah B, dan parentnya lagi itu A. Descendant child itu adalah yang di bawahnya, kebaliknya. Jadinya root A ini memiliki child B, C, D, childnya juga E, F, G, H. Ini tuh tapi cara tidak langsung ya. Karena secara teknis B itu child-nya E dan F, D itu secara teknis cuma punya child G dan H. Karena dia tidak tahu kalau ada I dan J di sini. Tapi kalau misalnya kita traverse, ya itu bisa dijadi child-nya. Nah, di sini itu ada apa itu ada dua menentukan apa itu level-levelnya di sini. Ada level tingkatannya ya. Di sini ada level. Level itu diukur dari root. Jadi ini dari root ini level 0, ini ada level 1, level 2, level 3. Lalu ada height. Height itu kebalikannya. Height itu uh, dimulai dari level yang paling terbesar. Jadinya kalau misalnya kita lihat di sini, I dan J itu levelnya dia paling besar. Maka dari itu kita bisa ide ini eh, apa itu height-nya dia bisa 0, di sini 1, 2, dan di sini 3. Dan kalau melihat di sini ya, ini E dan F ini itu tidak punya child ya. I dan J juga. Ini bisa dibilang leaf atau terminal nodes yaitu nodes node-node yang apa itu tidak memiliki children. Uh, dan ini E dan F, I dan J ini tuh memiliki parent yang sama, maka bisa dibilang kalau mereka itu sibling. Karena ya parentnya mereka sama. Lalu kita juga ada subtree. Subtree itu ya seperti namanya sub, satu bagian dari tree. Jadinya B, E, F ini bisa dibilang tree. Tapi dia itu kalau dalam konteks satu tree ini itu dibilangnya subtree karena dia tidak mencangkup seluruh tree yang ada di dalam ini. Bisa satu tree ini bisa bilang subtree, kemungkinan bisa dibilang subtree kalau dia itu merupakan bagian dari tree yang lebih besar. Oke, sekarang kita lanjut. Ini sudah kita tahu ya kan. Nah, apa itu internal node ini adalah semua node yang tidak termasuk leaf dan root. Jadinya apa itu B apa itu ada B, ada D, ada H ini itu eh, bukanlah leaf atau root tapi internal node. Dan koneksi dari ini semua, koneksi ini semua kita bilangnya edge. Edge itu adalah referensi yang menghubungkan antara dua node tersebut. Oke. Nah, kita sudah bahas itu semua. Nah, kita juga sudah tahu ya apa itu binary tree. Binary tree itu sebenarnya sama kayak itu tree, tapi dia punya dua kriteria. Apa itu uh, binary tree itu satu kriteria, sorry. Apa itu yaitu childnya cuma dua. Kalian lihat ya di sini. Satu, dua, dan tiga. Childnya cuma dua dari satu ini. Childnya dua, cuma ada dua. Childnya tiga, cuma ada dua. Begitu seterusnya sampai ini. Bisa childnya itu cuma satu. Misalnya di sini ya, aku hub, misalnya tree ini itu nggak ada. Eh, di bagian sini itu nggak ada. Ya udah, ini bisa dibilang tree. Tetapi kalau misalnya satu ini punya apa itu child lagi namanya n gitu ya. Ini nggak boleh. Ini bukan binary tree karena kita tahu childnya paling banyak dua. Nah, kita lanjut ke binary search tree. Binary search tree itu sama, tetapi dia punya kriteria lagi di sini. Kriterianya adalah subtree kiri dari sebuah node itu hanya memiliki key yang lebih kecil dari key node. Subtree kanan sebuah node hanya berisi node dengan key yang lebih besar. Dan apa itu subtree kiri dan kanan harus berupa BST. Jadinya sama kayak binary tree, tapi bedanya ya itu tadi. Ke kiri itu kalian harus bisa mastiin kalau uh, ini misalnya kalian mulai dari root ya. Apa itu children dari root kalian yang kiri itu harus lebih kecil, children yang kanan itu harus lebih besar. Jadinya kalian ke sini kiri itu lebih kecil, ke kanan itu harus lebih besar. Kalau misalnya kita lihat dari tiga ya, satu lebih kecil dari tiga, enam lebih kecil dari, lebih besar dari tiga, dan seterusnya, seterusnya, seterusnya. Nah, kalau apa itu implementasinya, mungkin kita sudah pernah nge-explore ini ya. Apa itu ini sama kayak tree yang pernah kita bahas di kelas, cuma ada BST node, apa itu kiri dan kanan. Lalu eh, setelah itu untuk find ya tinggal gampang. Kalau misalnya kita mau find, eh, kita itu tinggal traverse saja. Misalnya aku insert 7 di sini ya. Aku misalnya pengen insert 7 aku pengen find 7. Aku tinggal cek aja apakah key ini lebih besar apa itu nilai yang pengen kita cari itu lebih besar dari 8. Enggak, artinya kita ke kiri dan ini bukan sama dengan 8 kan. Ya udah. Oke, 7 itu apa lebih besar dari lebih kecil dari 3? Enggak. Artinya kita ke kanan. Apakah 7 itu lebih besar dari 6? Oke, ternyata iya ke kanan dan ternyata sama di sini. 7 itu sama dengan 7 di sini. Jadinya itu misal kita 14 ya, 14 di sini. Apakah 14 lebih besar dari 8? Pasti. Artinya kita ke kanan. Apakah 14 lebih besar dari 10? Eh, tentu saja iya. Ya udah kita ke kanan. Artinya ya 14, 14 dan 14 ternyata ketemu di sini. Kalau nggak ada dua kemungkinan antara angkanya tidak ada di situ atau kalian ngemasukinnya itu bisa salah. Em, misal kalau ini tak ganti 8 ya, ini tak ganti 7 ya. Eh, dan apa itu? Oke, enggak jadi. Aku salah tadi. Tapi basically konsepnya seperti itu. Implementasinya kita bisa menggunakan pointer, struct-nya ini kita sudah tahu ya. Nah, ini tadi kalau key-nya itu lebih kecil daripada root key, eh, misalnya di sini ya, sudah kita demonstrasiin ya. Misalnya kalau 4 ini lebih kecil ya kita ke kiri, kalau bisa ke kanan, kalau sama ya udah. Oh ya, satu kriteria lagi. Kalau misalnya eh, find itu kalau misalnya di BST itu cuma harusnya itu cuma ada satu nama yang unik. Sorry, bukan nama, value yang unik. Jadinya kayak integer atau karakter itu harus unik, nggak boleh tidak unik. Jadinya 8 duplikat itu bukan BST artinya. Oke, sekarang kita insert ya. Insert itu sama seperti tadi ya, sama sama. Kita traverse dulu aja. Misalnya ini 4 nggak ada ya. Kita traverse 8 itu apakah lebih besar dari eh apakah misalnya insert 4 ya. 4 apakah lebih besar dari 8? Enggak. Karena kita ke kiri. Apakah 4 lebih besar dari 3? Iya. Apa itu kita ke kanan? Apakah 4 lebih besar dari 6? Enggak, kita ke kiri. Nah, ternyata kiri ini tuh misalnya 0 ya kan. Ya udah, artinya kiri dari 6 ini itu jadi 4. Oke, lanjut. Harusnya di sini sudah aman. Kita bisa terus terus terusin aja. Nah, ini benar ya tadi itu pointernya. Remove juga sama. Remove itu misal ya kita di sini pengen nge-remove di sini, misal aku pengen nge-remove 6, kita harus bisa mastiin apakah apa itu kita harus bisa nyambung ini tuh. Apa itu di sini 6 ya. eh 3 ini kan nggak ada subtree lagi ya kan. Jadinya ya udah 7 kita hubungin ke 3. Atau apa itu misal aku pengen ngehapus mana ya kalau tree ya enaknya. Aku pengen ngehapus 6 di sini ya, tapi ada 4 udahan. Apa yang kita lakukan? Kita lihat aja fungsinya dulu ya tadi itu. Nah, kita cek. Ah, apa itu kalau rootnya dia left-nya 0, ya udah right child-nya itu jadi root right dan kita return right child-nya. Kalau misalnya ternyata right-nya itu 0, kita return left child-nya. Lalu kita assign baru di sini itu apa itu eh apa itu rootnya di sini ya kita cari yang paling kecil dulu. Jadinya kalau misalnya di sini 4 kan paling kecil, ya udah artinya penghubung di sini itu jadi 4 bukan 6 lagi karena dia paling kecil. Nah, ada juga di sini itu skew tree. Apabila insertionnya itu urut ya, kita bisa lihat ya. Kan ke kanan, kanan, kanan terus ya. Ya udah, ternyata kita skew tree. Ini tuh technically tree, tapi kalau kita lihat ya, ini cuma linear. Apa itu freak? Linear, uh, linear linked list. Seperti itu. Jadinya itu insertion pada BST itu sangat mempengaruhi. Oke, sekarang kita udah tahu ya, kita udah pernah bahas kan apa itu konsep BST. Tapi kita bakal maju ke konsep yang lebih advance yaitu eh traversal BST kita juga ada in order. Aku lupa. Ini kita bahas dikit. Ada in order. In order itu jadinya kalau kalian lihat ya di sini, oh ya Allah. Eh, apa itu in order di sini itu kalian ke kiri terus. Setelah itu print F, setelah itu baru ke kanan. Nah, ini efeknya apa? In order itu jadinya kalian dapetinnya itu urutnya itu descending. Apa itu urutnya itu descending ya, kalau seperti itu ya. Post order, kalian itu ke kiri terus, ke kanan terus. Nah, jadinya itu uh, urutannya jadinya seperti ini. Kalian dapetin uh, dari kiri kalian lalu ke kanan 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 terus jadi ke sini ke sini ke sini ke sini kenapa karena kita ke kiri terus setelah itu print setelah itu ke kanan nah ini 5 kita ke kiri dulu kiri nggak ada ya kiri kanan ya udah kita print 1 2 kanannya ada ya udah kita ke sini dulu traverse traverse oh ternyata ada 3 ya udah print dulu sekarang 4 nggak ada kanan ya udah kita print 2 nggak bisa nggak selesai traverse-nya ya udah kita ke print 2 seperti itu. Pre-order nah itu kita print dulu jadinya cukup urut ya urut dari root setelah itu kita ke kiri ya kan. Ah, print 5, setelah itu kita print 2, habis itu kita ke kiri lagi print 1, habis itu kita ke kanan print 4, setelah itu print 3, 6, 7. Contohnya bisa dilihat seperti ini. Oke, hopefully kita jelas soalnya aku pengen langsung pindah ke tree yang lebih advance yaitu self balancing tree. Untuk ini itu eh nah, di sini tuh self balancing tree itu menyeimbangkan dirinya sendiri. Kalau kita tahu ya, tadi itu tree itu bisa skewed ya kan. Nah, atau urutannya itu tidak benar, maka yang bisa kita lakukan itu adalah membalance-nya atau jadinya pas kita traverse itu pasti dapat angka yang kita punya. Eh, dan kita harus meminimalisir eh, tingginya. Kenapa? Kalau misalnya ini tingginya itu bedanya lebih dari satu, ya artinya tidak balance. Misalnya kayak tree di sini ya kan, itu tingginya cuma satu ya bedanya. Kalau kita lihat subtree di sini tingginya cuma satu, di sini ya cuma satu aja, di situ. Jadinya kita harus ngebuat dia balance. Nah, salah satu caranya menggunakan IVL tree. Dan untuk ini ASCII yang bakal jelasin. ASCII,
Hadir, wait, let
oke,
me share
kita
screen.
pindah dulu ya untuk share screen-nya.
Oke, aduh, share. Santai harus screen deh. Udah kelihatan belum? Wish.
Sudah, ASCII.
Wait, ini cara not annotate gimana ya? Kepencet. Enggak, oke. So, what is a file tree? A file tree is basically a self-balancing binary search tree. Now, kalau if you guys are wondering why are we using this, like, ugh, why? Uh, it's mostly about time complexity. So if you guys seen the skewed tree that a bit said before, like for example, 1 and then 2 and then 3 and then 4 and then 5, it's a skewed tree, right? Where uh it's like a worst case scenario for a BST, and it will take a lot more time to process for the program. So here the AVL tree relies on the height. So if it's what is the height? For exact, it's actually a number of node on the largest path from root to leaf. So like for example, I have this node, 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 and this node. So for example, the height for this full tree is 1, this 1, and this 2, and this 3, and this 4. So the height from the root to the leaf is 4, while this height is 3, this one is 2, and this one is 1. So it relies on that. And hold on, erase this. And then for the avial tree, the minimum of the difference between each height is only 1, like difference at most is 1. So here in AVL there is something called ish ba ay, wait, balance factor. So what is a balance factor? It is from it is actually like something you call the left height minus the right height. So what can you count as in FVL3 is that as long as the left minus right height is at least difference has one difference, for like maybe the left minus right is equals to either 1, 0, or -1. This was still considered as AVL. So here I think I can give you the example. Here, let me AVL3. I use Visual Go. So let me wait, create random. Okay, for 20 is a bit too much, maybe 15. And AVL tree has like many, what do you call it, scenarios. There's this balance where some of them has like a difference of one height, just like this 11 and then 32. The left one is one and the right one is two, but it still has only has like one difference, so it's still considered as AVL. While the others here, like 91, 72, and 92, 99 is considered as perfect balance. So for the perfect balance is here, where each right and left from wherever node it is, it's considered as balanced without any what do you call it? Without any distance, without any difference between each other nodes. So here's the minimal IVL tree. This is what I told. The difference at most is one, whether it's -1 or one. Here, from this left subtree, you can see it's the difference between the left side of three. The three node is actually 2 minus 1, and then for the 5 we have 4, and then yeah, they all have one differences. So what how does AVL work? So I will give you like a simulation. Maybe I could wait. Let me put the examples of balanced so it's easier. So for example, I will, oh, this 32 will be 35. Let's say I will insert 35. It will insert onto the right beside 32, right? So it will make like a two difference of balance. So it should change root until 20, see 29, 32, and this it will change to 35. See? Nah. So as you can see here, uh see, as you can see here, the difference node on the 29th is now changed into 2 since it doesn't have any left, what do you call it, left child at all, but the right child already has a height of 2. So this is not considered as AVL. How do we fix that? We change the, what do you call it, the child from 20. So they changed the 29 became the child of 32. Jadi node 29 itu berganti jadi yang awalnya dari anak si angka 20 itu berubah jadi 32. As you can see here. See. So now they are back to balance. And it goes same everything as that. Wait, let me try to create use the minimal AVL tree. So for example, I use 0. I don't know if I can. Okay, so it will go left, it keep left until it will be on the very left of the subtree. As you can see here, see, since this one has a difference of 1, so it's still considered. But the next one, node selanjutnya, node kedua, itu masih udah tidak bisa considered as AVL karena difference left sama right-nya dia. Yang left-nya misalnya 2, ini kan left-nya ada tinggi 2, sedangkan yang right-nya tuh dia nggak punya height sama sekali, so basically 0. It's not considered as AVL anymore. So what they do is make the 1 as the, what do you call it, the child of 3, and 2 bakal diturunin jadi anak yang buat pertama. Okay, for that, what do you call it, the concept explanation. Maybe does any of you have a question before we continue to the code explanation? I think that should be done. I will hand over the code explanation to Kenny or Fino. I forgot. Kenny ya, Ken?
I think
Halo?
it should be Kenny.
Oh,
Ya,
Kenny. Yes.
oke. AVL kan ya?
Yes.
Right. Wait. Oke. Halo, ini kata nggak screennya? Oke, jadinya
Kelihatan, kelihatan.
sekarang aku jelasin apa AVL3 singkatan dari Edelson Velocity and Landis Tree. Nggak usah diingat ini. Eh, jadi intinya self balancing BSD itu ada banyak jenis, tapi yang akan kita pelajari di sini AVL3 aja. Hmm, jadi singkatnya AVL3 itu BSD tapi bisa bisa gerak sendiri lah, bisa bisa balancing diri sendiri gitu. Hmm, balance factor ini tadi yang Mbak Aski jelasin yang kalau satu min satu atau nol itu masih dihitung balance, tapi kalau udah lebih dari itu maka dia nggak balance gitu. Nah jadi ada empat kasus. Pertama itu left skewed, nah ini left skewed. Kedua itu right skewed. Ke Keberapa nih? Ketiga ini zigzag begini. Kelima, keempat zigzag. Oke, pertama aku jelasin yang bagian rotasi kanan dulu ya, yang case left skewed. Nah, jadi intinya tuh left skewed ini kalau misalnya berat di sebelah kiri gitu. Nah, pertama-tama tuh kita itu eh, s- jadiin siapa 5 ini pivot node-nya karena kan node yang unbalance ini si 5 kan. Kalau 4 ini dia hitungannya masih balance karena dia ini min satu, kalau ini nol. Tapi ini dia min 2 atau 2 ya, nggak apa deh. Oke. Jadi ya node yang berat sebelah itu jadinya jadi pivot node gitu. Nah, jadi si 5 ini dia jadi bakal jadi right child dari 4. Iya, bisa lihat dari penjelasannya juga. Nah, ini tinggal pindah-pindah doang sih ini. Pertama, ini jelasin di kode ini new parent yang baru kan angka 4 ya. Jadi tapi pivot node left 5, pivot node left yang 4, jadinya 4 jadi new parent, pivot node left. Oh ya, nah semisal si yang ini si angka 5 ini punya anak lagi, jadinya nanti dia bakal dipindahin. Sorry, kalau angka 4 ini punya anak lagi dia bakal dipindah jadi left-nya si 5 gitu. Nah, bisa dilihat di sini, new parent right. Oke, nah kalau udah stabil, kalau udah kita left speed, kita bakal ambil tinggi tingginya untuk ngecek apakah udah balance atau belum gitu. Nah, oke. Nah, kalau right skewed ini ya apa kebalikannya yang left, sama aja. Nah, kalau yang zigzag ini. Nah, yang zigzag ini dia ini kan yang pivot notnya 5 ya awalnya. Kalau kalau misalnya kan dia ini kan eh, balance faktornya ini min 2, 2 lah. 2 ini satu, ini nol. Nah, tapi kalau lagi zigzag ini yang jadi pivot node-nya ini 3 dulu. Nah, ini kan bentukannya mirip apa ya? Dia ini kan kayak berat di sebelah kanan ya. Ya, right squid. Jadinya kita pertama di kodenya bakal ngelakuin, oh salah, nggak bener-bener, sorry sorry. Right rotate dulu. Setelah right rotate kan bentuknya ini left skewed kan, berat sebelah di kiri. Nah, jadi kita left rotate gitu. Nah, untuk yang right left zigzag ya sama lah, kebalikannya aja. Right rotate dulu baru left rotate gitu. Searching dan insertion. Nah, searching sama insertionnya itu mirip-mirip sama function BST yang Mas Abid jelasin, cuman bedanya itu, oh enggak, kalau searching sama. Tapi kalau insertion dia sama, tapi setelah kita insert, kita ngecek apakah dia balance atau enggak. Kalau enggak balance, kita apa namanya panggil function buat ngebalance ya. Ini kasus pertama yang left skewed, ini left right. Oh, zigzag, zigzag, ini right skewed, ini zigzag juga. Nah, bedanya itu kalau di AVL itu setelah kita insert, kita balancing tree-nya biar enggak berat sebelah gitu. Nah, fungsi utama AVL file. Nah, ini tinggal sama aja. Insert, oh ini apa ya? Ini helper function ini kayak ntar di redirect. Nah, deletion juga mirip-mirip sama BST. Find minimum. Oke. Jadi intinya ini juga mirip sama apa namanya sama function BST yang Mas Afi jelasin. Cuman ujung-ujungnya di akhirnya kita add balance factor. Jadi kita setelah hapus kan siapa tahu nanti ada yang nggak balance gitu. Jadi kita balancing tree-nya biar hmm, nggak berat sebelah biar nggak ngaruh ke searching time di big O notation-nya. Nah, ini. Oh, udah. Oke, setelah itu kita ke set dan map. Eh, oh, Vin, ini
Yo.
untuk selanjutnya bisa dijelasin oleh Mas Vino.
Okay. Hello. Wait. Can I share screen? All right. So, next up we have sets and maps. So, since you guys have already finished your midterms, you have unlocked a new superpower, which is the STL library in C++. This is very useful because you don't have to, what's it called? You don't have to copy paste the template from GitHub. All you need to do is just put this include, what's it called? This include line right here. And then you specify what type of data structure that you are going to use in the code. For example, this is set maps, and then you can use the insert, pop, and etc. functions. However, for now, we're going to focus more on sets and maps. So, what are sets and maps? They are a data structure that use self-balancing trees, whether it be AVL trees or red and black BSD trees, if I'm not mistaken. Uh, I don't know. They basically use uh the concepts of BSD and AVL trees by its own. It's already a set library from STL. So the difference between sets and map is that for sets they store a single value, which is a key, and for maps, they store a pair value, which is a key and the value. So for each key, it will be mapped to a certain value. So I think it's better to explain it while we code live. Hold on. So here are some basic functions of sets. How you can call it in C++ is you can use the include bit slash standard C++ dot H. Either that or you can include it manually, like include like set like that. But it's better to just use this because it includes everything by default. And then for sets, you would want to initialize it by using this line right here, set, and then you set the type of data that you want to insert for the set. It can be integer, it can be Boolean, it could be string. But for now, we're gonna do integer. And we have a bunch of functions for sets. For example, set.empty. This is just to check if the set is empty or not. If it is empty, it will be true. And if it's true, that means it's gonna print this out. And then after that, we have the insert function for the sets. This is like the push, like insert functions in what's it called? Stacks and queues. All you need to do is just uh, call the name of the stack that you call the name of the set that you already initialized, and then use the dot insert function. So for example, I want to name my set pool. That means all of this just becomes pool. Oop. And yeah, this is how you would insert it. And then if you were to print it, you can use a for loop. Same thing if you were to print out elements inside of a stack or a queue, you can use a for loop to check whether it's empty or not. And then it'll just print out one by one. So for example, if I run this code, is it running? Wait, hold on. Hold on, guys. As you can see, it'll print out all the elements in this set. A key note for sets is that they are not able to store duplicate values. So for example, if I insert 4 twice, it would print out 4 once. It should only print 4 once, as you can see. Sets, they do not store duplicate values. So it is a good data structure if you want to maintain or like make sure that there aren't any duplicate values within your data structure. And then this is a way to print the data ascendingly or descendingly. You can use the function from begin or from end, begin or our end. If it's a begin, then it's going to sort it ascendingly and vice versa. And then after that, we have defined function for the sets. This is just going to find this is just to make sure if the key inside of the set exists or not, and if it does exist, it'll print out, it'll output a true value, and if it's not, then it will output a false value. As in this example, we want to find 5, but since 5 isn't in the set, we print out data not found. Uh, Same as stacks and queues, we also have the erase function, similar to the pop and dequeue function from previous modules. This is just to remove a key from the set. And then after that, we have the maps. So for maps, they basically map out a key to a certain value. So for example, if you want to insert here, so for maps, the sets, you want to initialize it first using this line right here. Uh, you want to specify the data type, the data structure, which is a map. And then after that, you want to specify the type of data that you want to input. It can be integers, it could be character, string, booleans, doubles, etc. And then after that, you want to name your map. Let's just name it map for now. Actually, no. But yeah. So for maps, this is basically the key. And for each key, they will point to a certain value. So for example, here we have the key 1. For this key, it will point to value 2. So if you were to run this, for example, hold on. There you go. So this is how you were to print maps. If you want to print the key, you would do you would call the first, and then if you want to print out the value, it would be the second. And the same as the sets, we also have the find function. Again, all you need to do is just to say what's it called? The name of your map, and then use the dot find function, and then you input which value you want to find. So for here, it's going to find the value of key 1. So since this is key 1, it should return the value of 2. So if we were to run this, there you go. And then the erase function again. The same, all you need to do is just to um, the name of your map and then use the dot erase function and then specify which value or like which key you want to remove within the data structure. So this would remove this one right here. And yeah, it's been successfully removed. So I think that's all for now. Abid, should we explain the SDL in
Yeah,
general?
I think we should explain the HTL for now. Sorry that I wasn't using English before. Uh, okay, I will show you guys the process of uh, well, the STL because Sorry, wait just a bit. I will prepare my PC here. Now, I think everyone knows about the C++. I think it's already been demonstrated about the STL. But what we are going to do is to actually properly introduce on how to use STL. Hopefully, everyone can learn on how to use STL because uh, C, while it is really good, while C is really good at being fast, it has some limitation, and one of the things that it's limited on is on class and many other things, but and many various data types really. Oopsie, I have this. All right, so we're gonna start a bit fresh here. Before we end our today's session, we will learn about iterator. Now, iterator, uh, oh yeah, we already explained about STL. STL is a collection of template class for several function in data structure, which is a container. And iterator here is similar to a pointer used for well, it is used for accessing memory of STL data structure. From the, I think you already know about, I think everyone already knows about iterator in its name. Iterator means iterating it. So with an iterator, you start at the beginning of the data set, at the data, let's say in an array, uh, and then you iterate from the beginning until the end. Include std IO string, and then include, I forgot. Let me show potential pictures. Let me fix this first before I can give you demonstration algorithm. All right, this should be it. Now, every STL container has a pair of functions named begin and end. Begin is a function that returns an iterator pointing at the first element, while end is to the empty element next to the last element. Here is an illustration. Okay, you can see that it's begin, this is end. And both of them has their respective reverse version, R begin and R end, which is the reverse of that. When we what can we do is use it for sorting if you want to, but yeah, one of the things that it can do is we can pass it to an out. There is a function that sorts this. I believe it was a very advanced one. We already know about something like a divide and conquer method. It's something like that. Okay, um, we iterate through it, and then actually we just can run this, and as you can see, it gets sorted. And using R begin, we know about where it begins and R end where it ends. So yeah, let's try it. If we were to use begin and end, it will be sorted ascendingly. But if we reverse the input, that means it becomes descendingly. Okay, so auto auto is really useful, especially in C++, where you are required to define your own data type, right? And auto will automatically assign that variable into the data that is being given. So let's say I have auto here, right? I have auto a value. Now I cannot create an empty auto here, empty auto a value here because it needs a value to determine, okay, what should be the data type of this. So let's say I insert one. That means now this a value become an uh will become integer. Let's see. Now this can be very useful, especially if we want to like use if you want to use a very long variable name, something like that. Well, not variable, data type name. Look at this, like std vector in iterator pointer. What is that? I don't know. I don't understand this. But 3, 4, 2, 5, 1, 7. You can use this. We can just use this. And then, well, now a value knows that this is an array of either an array or a vector of numbers. What we can do now is auto pointer equals v begin. Now, a value begin. Now we get the pointer of this local variable constant and pointer, something like that. This is assigned to a variable. It means assigned to a list, either a list or an array, depending on what the compiler wants. Now, an iterator has several operators such as increment, decrement, but not all of iterator could be decremented, and dereference. Yeah, STL comes really handy for your FP later because you don't have to copy paste. That means with STL, you don't have to copy paste about your data type. So let's say I want to data type or function. So if I want to use stack, I can just import stack like this, include stack. Like, how easy is that? I don't have to copy anything. Let's say I have a stack with an int and a stack like this, right? And I can just call it a stack. A stack just push 10. How easy is that? I can just do this. I don't have to initialize any kind of code, which is amazing, really. And then, yeah, we can continue on this. We can use it with increment. Oh yeah, since this is just a regular pointer, let's say cout. Oh yeah, already. A pointer. Let's see if this works. Let's see if this works. 3, right? Because the beginning here is 3. But let's say with the concept of pointer, right? You can just increment this. And then, oh, okay. I think I should be doing this. Yep, there we go. The pointer is now incremented. And now I can just point to a new one, really. Now with increment and dereference, increment and dereference here, we can also access every element of the STL container without having an empty STL container, because this is just a pointer. It is really good because other the well other languages don't give you this pointer, and so you can just print. You cannot just willy-nilly um, print anything really in this case. Willy-nilly something uh, like access the array, you know. Well, in Python, if you want to access this, we can, you have to iterate through it every single time, but here you can just use a pointer to reference. Oh, this is the middle of the array. Let's just use that. Yeah, there we go. And yeah, that's basically it. So, anything else to discuss here? Oh yeah, I will open. Oh yeah, thank you. Okay, before we go to next agenda, are there any questions? I will open the question for 5 minutes maybe, just to give us some breathing room too. Oh yeah, for the lab work next week, you are free to use anything really. You can use the C or C++ code, but only in the range of that. Okay, because the code will be submitted to Tom Judge. Use it will be submitted to Tom Judge, and yeah, that's basically it. For FP, I think it's probable to use C++ because C is quite limiting in terms of its STL capableness. Yeah, so just use C++. But if you're still comfortable using C, that's okay. It's up to you. You're not limited. Hopefully, you're not limited. Yeah, just that C and C++ have different capabilities.
Ya, sekarang aku pengen demoin dikit cara make ta- cara make apa namanya eh AVL. Ya, gampang sih, tinggal panggil-panggil aja. Pertama, kalian harus initialize dulu pakai ini. Katakan screen share-nya ya.
Aman-aman.
Oke, AVL, AVL ku atau AVL aja boleh, bebas. Harus di initialize dulu. Terus coba lihat ada apa aja ini. Ada, oke. Kalau mau insert tinggal panggil AVL insert, terus insert angka berapa misalnya. Angka coba kita lihat. Oh sorry, pertama kita harus setelah kita declare apa namanya, declare AVL, kita harus initialize dulu AVL, AVL. Nah setelah kita initialize, kita baru bisa insert insert misalnya satu satu. Terus kalau misalnya pengen ganti jadi karakter juga bisa. Oh iya, kalau misalnya mau ganti karakter di karakter ya, ini berarti kita harus ganti jadi char ya, char. Terus mungkin aku nggak tahu ya, praktik mungkin nanti ada yang pakai karakter gitu mungkin. Terus kalau pakai karakter nanti harus ada yang di apa ya, di adjust juga, diganti-ganti misalnya di mana, Ini in aja jadi char kan, jadi char. Terus value-nya pakai apa ya? Kayak tetap bisa. Oh, kayaknya kalau karakter tetap bisa di apa namanya? Pakai ini, pakai apa namanya? Operator ini nggak usah pakai star compare kayaknya. Ntar mungkin juga bisa eh datanya isinya bukan karakter tapi string saya juga. Nah, kalau pakai string nanti pakainya star compare gitu. Tergantung soal. Web work itu ada yang kalau aku dulu praktikumnya ada yang pakai karakter. Nah, kita sekarang pakai pakai in aja dulu ya. Error di mana nih? Bentar, nggak kelihatan. Error di mana? Type in. Oh, wait, wait, wait. Oh, iya, iya. Oke, lupa ininya. Bentar, rapihin dulu. Kita perlu, ya, ya, ini harus saya, ya benar. Terus kalau udah insert satu ABL 5, 8, 2, 3. Terus kita bisa void, kok void, pre-order ABL, pre-order ABL node root. Oke.
Itu initnya nggak pakai dan AVL kan?
Hah, iya
Cuma
kan?
init terus ya dalam kurung doang.
Ini,
Ya.
iya kah? Ini ada ini.
Wait, ini sih atau C++?
Oh, gue pakai yang C.
Oh, sorry, sorry. My bad.
Sorry, sorry. Ya, aku sukanya kalau tri masih suka tetap pakai C. Aku baru pakai C++ waktu yang graph. Oke, tak, kok gue lupa cara manggil ini gimana ya? Reorder, reorder node root. Mana? Eh, Reorder. Tak, cek bentar, agak lupa-lupa. Eh, ini, oke, bentar. Hmm, ya, oh, bisa. Oh, lupa. Nah, iya, nggak bisa kan? Dari mana rootnya ya? Oh, oke, wait, 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 wait. Oh ya, sorry, sorry. AVL, AVL node. Oh ya, oke. AVL, oh, ada. Nah, ini. Oke. Iya, harus pakai apa? Kita kalau mau pre-order kan ini kan karena dari root ya, jadinya kita ambil dari sini. Karena mereka cuma tahu rootnya doang, baru di traverse nanti. Nanti traverse kan pre-order ya. Kalau misalnya in order nanti nggak ngaruh ya. Oh, bentar, ngaruh. Oh, ngaruh ya. Oh, apa tuh? Oke, oke. Oh my God, tinggal lu ubah aja. Ini pre-order aja. Oke, kalau udah insert ada lagi apa lagi? Fine, fine ya. Kalau fine itu nanti dia returnnya true ya. Jadi misalnya kayak cuman if ABL fine angka 3 misalnya. Oke, ya, ada angka 3 gitu misalnya. Kayak gitu kan ya makanya ABL fine. Oh, perlu ini juga ABL. Nah, ya kayak gitu. Itu buat ABL fine dia returnnya boolean ya. Terus is empty. Is empty ya mirip stack dan lain-lain kosong atau enggak. Init, insert, remove. Remove nih. Misalnya ABL remove panggil panggil tree-nya sama info 8 misalnya. Terus kita print lagi order. Wah, salah. Nah, angka 8 hilang. Terus kalau udah ada apa lagi? Order, insert, remove udah semua kayaknya. Ya itu dong sih. Init, insert, remove, pre-order, sama find. Ya tadi find juga udah, sama is empty. Nah itu kira-kira untuk cara memakai ini. Ntar kalau misalnya mau ganti jadi char, ganti di sini jangan lupa sama ini innya ganti char, ganti char juga di sini. Nah kira-kira gitu. Sesuaiin aja. Ini juga bisa string nanti ya apa namanya, tergantung yang buat soal lah. Ya bisa string ya. Ntar kalau string kita balancing faktornya ini. Balancing faktornya kita ganti star compare nanti berarti bukan pakai apa? Bukan pakai ini operator lebih besar sama dengan lagi. Oke, oke. Ya, jadi itu untuk cara pemakaian trivialnya bisa dilanjut. Habisnya apa habis ini? Halo?
Halo, mungkin Vino ada yang mau ditambahin?
Hmm, for now, kalian masih ada yang bingung nggak tentang apa yang kita jelasin? Tentang konsep AVL3 mungkin?
Kita tunggu 5 menit dulu aja ya, lagi buat ini. Ada pertanyaan langsung aja. Kalau nggak chat, raise hand aja.
Okay, everyone, since we have quite a lot of time on our hands, about an hour-ish, so I think since we've already explained the basics of AVL trees, we can send you guys some questions. We're going to send some questions in the group for AVL trees. Hold on. I'm gonna give a brief explanation, then we're gonna give you guys 15 to 20 minutes to do it. Hold on. Okay, we sent you guys some questions in the group. One is very easy and one is a bit tricky, but we'll get there. I'm gonna explain the first one, which is the problem is basically to balance a binary search tree. So this is like still pretty basic. Given the root of a binary search tree, you want to return a balanced binary tree with the same node value. Um, so basically, with this input like 1, 2, 3, 4, since this is a skewed tree, um, how would you be able to like make it balanced? So for example, this is pretty skewed, right? Um, so the balance factor for these would be, hold on, I think, let me just visualize it. So for example, we have, wait, okay. Whoa, that is not it. There you go. Want to insert one, insert two. As you can see, whenever we insert, the balance factor is going to be updated, right? Let me insert 3 again. As you can see, when 3 is inserted, the balance factor for 2 increments and for the root increments also. So whenever there is an imbalance with the balance factor, it is going to determine whether it's going to make a right or left rotation, right? So when we insert 4 to insert it, oh, oops. So when we insert 4, it should go to the right. But since the balance factor has been incremented and it's not balanced, there's an imbalance in the balance factor, it's going to, oh wait, I see. But yeah, I think for this question, just you can use the template from the GitHub so that you can see whether it can be balanced or not. And if it's not balanced, try to balance it using the code from GitHub. I think that's it for this question. Abid, do you want to explain the next question?
Okay. So for the next one, it will be this. Sorry. Yep, there will be this. So a column conundrum. Now, we already know that the tree has a row, right? This is level one, level two, level two, and then level three. But now, the question is, I want this question asks that you print the row of the tree itself. Uh, I'm sorry, the the column. So we see that this tree itself is a column, right? If I were to annotate this, so this is column one, this is column two, this is column three, and this is column four. I did not make a straight line. Good Lord. Where do I draw a line? There we go. So this is column one, this is column two, this is column three. This is column four, this is column five. So one, two, three, four, and five. So what this question asks is to print the total amount of value inside of this column. So let's say in this tree, right? Column one will have a value of one. Column two will have the value of two. Column three have a value of seven. Column five have one, two, three. Column four has a value of five, and column 5 has a value of uh 6 6, yeah. So but let's assume that the root itself is column 0. So that means this one is column -1. This one is column -2. -2, -2, -1. This is column 0. This is column 1, and this is column 2. There we go. Now, print the value from the leftmost column to the rightmost column, and then, yeah, that's basically it. So it's quite simple in theory, but quite a bit tricky if you quite a bit tricky, but it should be quite easy once you know how to do it. Okay, so I'll give you maybe 20 minutes to solve either one, and then we'll give you the we will discuss on the solution for a question that we just gave you. Okay, are you guys clear? Okay, hopefully that's clear. So 20 minutes from now.
We also want to re-explain again. So uh, one of your friends asked about how balancing factors work in AVL trees. So AVL trees are basically BSTs, but balanced, right? But how can you determine whether it's balanced or not? Uh, you determine it by using what is called a balance factor. How you calculate a balance factor? Am I sharing my full screen? Wait, hold on. So how to get the balance factor? If you see the code here from the template, it returns the balance factor by subtracting the left height from the right height. So if you guys remember, for trees, the left one is usually the node with the less value compared to the root node, and then the right one is the node that has more a bigger value compared to the root node. So uh, you basically calculate the height of the children, the left child and the right child. So for example, for this one, uh, it's 3 minus 2 because this height on the left is 3. So it starts from 0, 1, 2, 3. And then from here, it's 1 because, wait, sorry. It's 1, 2, 3, and then this is 2 because 1, 2. And if we subtract it, it is going to be a plus. And if the value, usually the values are either 0, 1, or -1. So if it's a 1, you would want to make a right rotation. So 50 would be placed over here and 100 over here. So yeah, let me visualize it again. So let's say we want to insert 5. It's going to the right. It's going to keep going to the right because 5 is bigger than all of this. The height is going to update. There's now 2. There's now 3. And since there's an imbalance, we do a rotation like so. If you guys are still confused about rotations, you can just use this website right here to visualize rotations much better. I think that's all. Okay, guys. Has anyone finished it yet? Because if not, we'll do a quick demo on like the solutions for this one. So we want to print out the balanced binary search tree, right? As you all know, for the template from the GitHub, it automatically prints everything. It automatically makes the balanced tree, right? However, the output is only for in order. So it's going to only output like 1, 2, 3, 4 like this. So uh, how to make the output as the question requires? Uh, you can first reverse it in order first. So if it's in order, it's going to output 1, 2, 3, 4, right? Wait, it's going to output 1, 2, 3, and 4. Um, we can then make a balanced binary search tree to divide this in half and then set this as like a root. So for this example, we make 2 the root, and the left here, 1 becomes the left child of 2, and then this part right here becomes the right child of 2. But then since we still have 3 and 4 right here, we can do it recursively. So we divide it in half again. So 4 becomes the right child of 3. So once it's built, it would look something like this. 4. However, this isn't the only correct answer because it can also be done like this. 3 as the root. So for example, if you do it again, hold on. We can also make 3 as the root, which would also be valid. So for example, we make 3 as the root. So that means 4 becomes the right child of 3, and 1 and 2 becomes the left child of 3. Since this is still imbalanced, we can divide it again, and then we make 2 as the root, and 1 becomes the left child of 2. If I'm not mistaken. So it could also be like this. But I think in the question, in the example, 1 is the root, which can also work in this case. So 1 would be this for here. And since 2 is bigger than 1, 2 goes to the right. As seen here. Uh, Another example can be 2, 5, 7, 8, 10. We can divide it as so. 7 becomes root, and these 2 become the left and right child, and then we do it again. Example 5 becomes the root, and for 8 and 10, 8 becomes the root, 2 becomes the child, 10 becomes the child, and so on. So it would look a bit like this. And for the second thing, since it's 1, 2, 3, it would automatically be balanced as 2, 3, 1, 2, 1, 3. So the output would be the same. Here's the code of the logic that I just explained previously. We divide it in the middle first, and then from the left and right, we then insert it into the left and the right to build the balanced binary search tree. So yeah, I think that's all for my explanation for this question right here. If you guys still haven't finished it, uh, you guys can finish it during your own time because this can be a good exercise to just grasp the basics of how balanced binary search trees work. So I think for the next one, Abid, can you explain?
Okay.
Mas
For the
Abid.
next, sorry. So for the next question, I will attempt to explain it. Oh, no, not that. Where is it? Okay. Hold on. Let me stop my screen share first. I will prepare the question. There we go. Ah, there it is. So, for the next one, so how do we determine this column? Continuing from before, right? How do we determine this column and get the value of each column? Well, it is actually quite simple. We just need to make, we need to store the column outside somewhere else. And to do that, it's actually, I'm using a map in this case. So if you guys know a map like before, a map is a key, right? It uses a key to store a value. And since a map is zero initialized, so we don't have to initialize it further. And for that, what we can do is actually traverse the tree itself. Let's say I have a tree here of 4, 2, 5, 4, this tree, right? 4, 2, 5, 1, 3, 6. So what we can do is count. We start from 0. Okay. We start from 0, 4, which is the root, which is column 0, right? And so we can use an in order for this. Any type of traversal will do because in this case, what we want to do is just to determine to enter the value of the value into the column. So how do I say this? Here we have we just reverse the West reverse first. So let's say we start at 4. This is column 0. So at column 0, we insert into the column map at the value of the column, and then we add the value of the column itself. So 4, we insert that into the total value of the column in the map. This is the key, and this will be the value of it. We added. So let's traverse to the left here. Oh yeah, let's traverse to the left. At 2, at column -1 here, we have value of 2. That means we will add that into the map. So column -1 will be 2, and then -2 column -2 will have a number of 1. Column of -2 will have the value of 1. So now we go back to 2, and then we go to 3. 3 is the column of uh 3 is the column of 0, right? Because this is 4, this is 4 is column 0, 2 is -1, and then if we go to the right, that means we go to the column 1, column 0, sorry, in this case. So we add 3 into column 0. So now column 0 has a value of 7. Now we go back into column 0 and then go to column 1. Column 1 has a value of 5 here. So we add that into the map. And then column 2 will have the value of 6. So we just add that into the column. So how do we do this? First, I will set the map here first. And then using I just copy pasted this and then created a new function here. Now this function will hold the pointer of the current node that we're traversing, the map, the pointer to the map. This is the pointer to the map, and then we have the column. Column will be incremented and decremented depending if we go to left or right. So let's say I want to. So in this illustration before, I just gave you. Where is a pen? In the illustration I just gave you, we start at column 0. So we start here at column 0. And then if we go to the left, that means we are decrementing our column value. So here, column will be decremented by 1, decremented. And then if we go to the left again, that means our column value will be decremented again. If we go to the right of the tree here, that means our value will be incremented. So this will be 0. And then if we go to the right here, we will turn to the root here. That means this one is column 1, incremented, incremented. So that's the general idea of the traversal. So this order can be any order, really. It can be in order, pre-order, post-order, just so that just increment this correctly, and then we insert it into our value. Now we have a array of a massive. This is technically vector. So since in a map the key itself is randomized in this position. So we don't have exactly you don't have it exactly in like a sorted order. So what we can do is sorted it from uh, the smallest key, so the leftmost one here, into the rightmost key, or the biggest key. So this one is column -2, so it will be the smallest. Column -1, the next one, column 0, column 1, column 2. We use the sort function that we just used before, and then we print the value of the column one by one. That's it, really. And then, well, we just print end here. So let's demonstrate it here. Okay, so if I were to copy paste this, as you can see, if we insert 1, since the value of the tree is only 1, that means it's 1 here. Insert 2 will, if we solve this, that means column 0 will have the value of 1. So if we insert 1, that will be 1. And then if we insert 2, that means the value will be 2. The next column will be 2. So if we insert 3, it's going to be like this, right? Well, that is not correct. So what we can do, the AVL will put it like this. But since the column is still from the smallest key to the biggest key, smallest to largest key, that means we still print it like 1, 2, 3. And then if we want to add another key, we can just add another key, another value here at the -1, 0, 1, 2. This is the second column. And then if we want to add 5, that means the arrangement will be different. And yeah, and so on and so on, something like that. So the key here is to use traversal and then storing the column value during this traversal. And then once it's complete, and we can print the value based on the smallest key to the biggest key. So you guys understand this? Are there any questions before we end this, I believe? No, I don't believe we ended. Okay. I think I'll press this to this is the result. So, thank you guys. So before you guys leave, I want each and every one of you to I will take a screenshot of this first. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. I want to all of you to rename yourself to with your NRP and your name first before you leave, or maybe not. You know what? I want all of you do that first, and also before that, I want you to. I will check your presence here if during your rename. Okay, so Papalia Mialam
Here.
okay, Muhammad Ilis Rusdi, Muhammad Ilis Rusdi,
Tadi dia masuk tapi izin leave.
okay. Ramsyasi Ahmad Syabri, Muhammad Ramsyasi, no, okay. Muhammad Arifatan,
Hadir.
Bismantaka Revano, Bismantaka Revano, halo,
Hadir, Pak. Hadir, Mas. Sorry.
baik Mas. Stefani Gabriela,
Ya,
Kenzi, oh yeah, I forgot to turn off this recording.